Greetings and welcome, class. Today we're talking about, what were we talking about? Sum and difference identities, of course, on page 442. Question 17, the direction said, use the sum or difference identities to find the exact value of each trigonometric function. So sure, you could just plug your calculator into radian mode and type this in and get a decimal approximation, but who wants that seriously? Well, probably engineers and people who are calculating sine at this radian angle, whatever. But so sine of pi over 12. Let's talk about pi over 12. Pi over 12 is equivalent to what? Well, let's see. Pi, in terms of, if I wanted to convert this to degrees, all right, I would multiply by 180 divided by pi. I don't know if you guys recall that little trickaroo. The pi's would cancel out. And between both of those, I think 12, does 12 just straight up go into 180? I think it does. Well, let's assume we don't know that, because I don't want to just jump the gun. Let's say 6 goes into 12 twice, and 6 goes into 180 30 times, right? I believe so. And 30 divided by 2, oh, wait a minute, I know that. That's the same as 15 degrees. Okay, so if you're not a super master of the radians, I still want us to do this problem in radians. But I just want to point out 15 degrees, I don't have, when I'm using the hand trick, I don't have a 15-degree finger. But 15 degrees is the same as 45 minus 30, okay? And those fingers I do have, right? And if I want to represent that in terms of radians, that means pi over 12 must equal 45 degrees is a quarter of 180 degrees, or pi over 4. And 30 degrees is a sixth of that. So, so this is the actual setup that I'd be working with there. So sine of pi over 12, sine of pi over 12 is the same as sine of pi over 4 minus pi over 6. All right? Right. So, looking a little more at this here. Wait a minute. Sine of the difference, two angles, sounds like a difference identity is what I'm going to use here. So I'm going to have sine of, let's see, where was it? Alpha, here we are, minus beta. Let's see, and which one's that one equal to? Sin cos, cosine, let's see, so that was sine alpha, cos beta, right? And then it's, is it minus or plus, friends? Minus. For the sine one, it matches. For the cosine one, it doesn't. And this is then cos alpha sine beta. So this is the little formula that I'm using. So alpha I'm referring to as pi over 4. You don't have to label that necessarily, but alpha is my pi over 4. Beta is equal to pi over 6. Actually, technically, I bet you could plug in, you could think of this as plus the negative angle there. And you could make beta negative that if you made this positive and positive. But who would really want to do all those extra calculations when I already have them written as angles in quadrant 1? Am I right? I'm pretty sure I'm right. So this is equal to sine alpha. So that's sine of pi over 4 multiplied by cosine beta, cosine pi over 6, minus cosine alpha. So that's cos pi 4 times sine of beta, which is pi over 6. So let's see if my hand trick can help me any here. Pi over 4 is my 45-degree finger. Don't ever give anyone the 45-degree finger. Cosine of pi over 6, that's 30 degrees. That's root 3 over 2. Minus cosine pi over 4 is root 2 over 2 multiplied by 1/2. Okay, so this is root 6 over 4 minus root 2 over 4. And those have a common denominator, so I can write this as root 6 minus root 2 all over quattro. And my answer agrees with our libro. I think I'll take it. Good stuff. So this is an exact answer to that trig function, the value of sine of pi over 12. It is not a decimal approximation. Okay, so. Yeah, to convert from radians to degrees, you multiply by 180 over pi. To convert from degrees to radians, you multiply by that reciprocal pi over 180. Yep. So let's look at un otro problema. Let's see, maybe for this one actually I might not do the whole thing. Let's see. But so 23 pi over 12. I don't know if you guys realize this. Let me actually do this kind of in as many radians as I can. That is like right here. Pac-Man again. So that's 23 pi over 12. All right, because 12 pi over 12 would have been a half circle, right? 24 pi over 12 would have been a full circle. So question for you guys, what is the reference angle right here? Yeah, that's pi over 12, or in this case, well, yeah, kind of negative pi over 12 is a coterminal angle with it, but pi over 12 is the reference angle. Let's see, I'm calculating tangent. Is tangent positive or negative in this quadrant? Negative. Because sine and cosine disagree. So yeah, tangent is, I believe this is the polarity of the tangent function in its respective quadrants. So I'm going to break this down into, well actually, should I do that first? Or no. Better yet, guys. I could actually have written this as negative tan of pi over 12 and gone from there. But this might actually be interesting. Oh, no, I'd still have to end up doing that work anyway. I was going to say I could have written this as the tangent of 2 pi minus that. Or, minus this would have equaled that, and that would have worked as well. Well, let's do this as this. Equals negative tan of pi over 12. And I believe just on our previoso problem, I realized that pi over 12 was the difference of pi over 4 and pi over 6. So this is equal to negative tan of pi over 4 minus pi over 6, which I think I can use a done identity there for that. What's up? Question?
How would we know pi over 12 is equal to pi over 4 minus pi over 6?
Well, I ended up demonstrating that by finding out that's 15 degrees. 15 degrees was 45 minus 30.
Couldn't you just make it into degrees without having to break down?
You could, but I want us to be really familiar with radians. Eventually, I'm hoping that you guys would be able to just, straight up know radians, because I'm sure your calculus teachers and professors would appreciate it. No. I wouldn't mark you wrong on a quiz for converting to degrees to help yourself figure this stuff out. I mean, that's fine. That's fine. So let's see my tangent formula. All right, this minus sign, the tangent difference identity that I'm going to use, is going to be replacing this portion here. Okay, so this minus sign is unrelated to that formula. So this is going to equal tan alpha plus or minus tan beta. So it's going to match in the top part. So this would be tan of pi over 4 minus tan of pi over 6 all over, and in the denominator it's going to be 1 plus, because it's the opposite for the denominator from this sign. All right, getting this right off our little formula sheet. Tan alpha times tan beta. All right. So let's calculate some of these. And this minus sign is technically applying to the whole thing, so I can just wait to opposite this later if I wanted to. So equals tan of pi over 4, that's 45 degrees. That's when tangent's equal to 1. That was a wobbly vinculum. I think that sounds like a cool band name, wobbly vinculum. I imagine it would be like some sort of dubstep band, like techno, electronica, bit tunes, chip tunes. That's what chip tunes is when they take old console, Game Boy or Super Nintendo parts and like take those chips and like make like a DJ board out of it, so then they can like use video game sounds of like 8-bit music in order to make their own music again. It's pretty interesting stuff. But anyways, tan of pi over 6. Pi over 6 is 30 degrees. Tangent's 1 over the square root of 3 in that case. And let's see, 1 plus tan of pi over 4 is 1 multiplied by 1 over root 3. Right, because tan pi over 6 again. Let's see if I can figure this out here. So this is equal to the opposite of 1 minus, I'm going to write that as root 3 over 3 maybe, all over 1 plus root 3 over 3. And now, really, from this point on, it's just a matter of how comfortable we are in dealing with radicals and denominators within denominators, because I've got a complex fraction. First thing I'm going to do, let me deal with these denominators, is what I call them. The way you deal with the denominators is you find the LCD of all the denominators. So between 1, 3, 1, and 3, what's the LCD? It's 3. So I'm going to multiply top and bottom by 3. And what's cool about this is going to kill the mini fracts for me. Multiplying by 3 over 3, that's the same as multiplying by 1. So that's completely allowed, a legal mathematical move that I can do. So I'll have negative, and now it'll be 3 minus the square root of 3 over 1, no, sorry, 3 times 1 is 3. Here the 3's cancel out. 3 plus the square root of 3. But I still have a radical in a denominator. How do I get rid of that? I think I briefly showed this to you yesterday. You multiply. Now the fact that if this was just like a square root of 3 here, I'd multiply by rad 3 over rad 3, and I'd be golden. But the fact that it's composed of like some sort of almost binomial thing, I end up having to use this pattern, a squared minus b squared, which comes from a plus b times a minus b. All right, this is called complex conjugates. If I multiply by the conjugate, all right, which is not quite the same, not quite the opposite, it's just the middle sign is different. That's what makes a conjugate. I feel like I almost had a song going there. I'll have to work on that. So let's see, equals the opposite of. Multiply these out. That's actually a pattern as well. I'll tell you what, let me throw that pattern at you. A squared, those are minus signs, minus 2ab plus b squared. You, of course, have these patterns memorized from childhood, I'm sure. Well, we're using the minus version here. So I'm multiplying it by itself, so I'm going to use this side of the pattern there. So I will have negative of 3 squared is 9, minus 2 times 3 is 6 square root of 3, plus the square root of 3 squared from this b squared is just 3. All over, and in this denominator, a squared minus b squared. 3 squared is 9, minus root 3 squared is 3. Notice getting rid of said denominator's radical. So, up top, combine like terms. So I'll have negative of 9 plus 3 is 12 minus 6. Rad 3. All over 9 minus 3 is 6. And I'm going to deal with this minus sign in a moment here. I'm running out of room though. Notice that I can actually reduce this, and this all by 6. If I'm going to reduce, I have to reduce every term in the numerator by 6. Also notice I'm not reducing the rad 3. It's part of this single term here. And I couldn't do that anyway because the radical can't cancel out with a non-rad. So I'll have negative of 12 divided by 6 is 2, 6 divided by 6 is 1, and I believe I can now distribute my minus sign and just get negative 2 plus rad 3. Did the book write it that way, or did they write rad 3 minus 2? No, negative 2 plus rad 3. Guys, we're on a roll here. I like it. I like it a lot. So pretty much from this point on, this was all fraction work and radical work. All right, so like two concepts that you might need to go back and refresh on a little bit in order to have your algebraic manipulation skills up to par, so to speak. All right, so here we go, 27. All right, pick up the pace here. Here we go. Represent. Cosine x minus y. The formula is Let's see. There's only one of them. It's equal to, that's going to be cos x, cos y. And the sign is going to be the opposite of that one. It's plus sinc sin e. Now, notice I know the value of cos x is 3/5. I know the value of cos y is 4/5. I do not know the values of sinc and sin e. Now, I believe this problem had additional directions. They basically told us that x and y were both between 0 and pi over 2, which tells me I'm in quadrant 1. Okay? That fact is merely going to be helpful for knowing the polarity of some of my terms here. All right, in order to find sine x and sine y, yeah, I can link this to sine x using a Pythag identity. I can link this to sine y using a Pythag identity. Okay, so it's just going to be a matter of doing that. So the Pythag identity is sine squared theta plus cos squared theta equals 1. And to find sine x, let's say, I would say sine squared x plus cos squared x would be 3/5 all squared equals 1. Sine squared x plus 9/25 equals 1. Sine squared x, if I subtract 9/25, what's that going to be? Is that 16/25? I believe so. Were they oh so kind to us? Oh, yes, they were. Root both sides. Root plus or minus, technically. And I'm going to get sine x is equal to 4/5. Now, question. Was this positive or negative? Well, if my angle's in quadrant 1, I happen to know that sine is going to be positive, so I can ignore the minus part there. So I get sinc is equal to 4/5. Let's see, similarly for cosine or sine y. Did anyone calculate this that I could just go off of that so I don't have to? All right, so you went down and you ended up getting sine y equals 3/5. And I believe I agree with that. Yep. So so if now that I have this, and this, I can just merely plug it into this long equation, and I'll get cos x minus y is equal to, what were the first two? 3/5 and 4/5 plus sine x times sine y. Right? So equals 12/25 plus 12/25 equals 24/25 is cos x minus y. That would do it. That would do it. Okay. Let's take a look at one last problem. Wouldn't be a good math homework assignment if we didn't have to verify some trig identities, huh? So, behold, we've got sine of a plus b. That's a sum identity for sine. We can substitute that since now I know an identity that can replace that. Let's just replace that side, I'm guessing. Like I said, with this verify stuff, you just tinker at it until you can kind of get them to meet in the middle, hopefully. So let's see, sine of a plus b, that's going to equal sine a cos b, cos b. Plus sign here, matches, yep, for sine. And then this would be cos a sine b. Equals. What do you guys think? Should I break it up? Oh, break up the fraction into two denominators? You could do that. That might be interesting. And do you think I should write these all in terms of sine and cosine? I'm guessing
Yes.
Probably. So let's do a bunch of that. So I'm going to rewrite tan A as sine A over cos A. All right. And I kind of like the break it up idea, I think. But let's see what happens first. We'll make sure everyone's following along. Plus, tan B is going to be sin B over cos B. And then I'm dividing all by secant A is the same as 1 over cosa times, I guess I should specify that these are being multiplied, and sec B is cos B. Actually, we might not have to do a break it up thing here. I could just multiply the numerator by the reciprocal of this denominator, because this is really all just one big fraction here, right? So yeah, so let's do that. So sin A cos A. But your break it up tactic would also work. That would be interesting as well.
I meant break up tangent.
Oh, you meant like break it up into those?
Yeah.
Okay, all right. That similarly works. So I'm going to multiply this by the reciprocal of the denominator, which is cos A cos B. Right? And in doing so, I'm going to get, here the cos A's would cancel out. I'd have sine A times cos B. And here the cos B's would cancel out, and I'd have sine B times cos A. And it's plus. And I'm comfortable with calling that verified. Sure, this is flipperood, but commutative property, friends. Commutative property. We're good with that. So that's verified. Whew. This was a long going over the homework video. I'm guessing this homework probably also took a long time. Well, thank you for your diligence, friends. Have a great day. Bye-bye.